Let's talk about thermodynamics. And probably you've heard this before. It's about the energy related between work and heat. We're going to be talking essentially about processes because there's thermodynamics about anything. Thermodynamics in chemistry, very like fundamental atoms, how energy and microscopic states. We are more interested in the macroscopic state. And please imagine I show you this image. As I said you before, I want you to imagine what do we engineers need thermodynamics for. So click pause, try to think what in your house or what in your daily life you see and there's thermodynamics in there. So what do we cover generally speaking in thermodynamics? And of course, there are plenty of syllabus. I saw, for instance, applied thermodynamics. They see a lot of microstates, which I don't think is worth it. The typical one is macrostates. We are interested in equipment and processes. And eventually they go more for substance thermodynamics and chemistry thermodynamics, which once again is pretty similar to micro, between micro and macro. I personally think it's of most use to understand the macro level. So we start typically with the type of systems that they are open, closed, isolated, and so on. Once again, the concept of enthalpy, which we already cover in energy balances, but typically energy balances and thermodynamics are either in the same semester or one after another. Now we cover a lot on temperature, that is a variable. Intensive variable does not depend on the amount of mass. Q, or heat, does depend on the amount of mass. So this does not depend on mass. So the more mass, more heat. The more mass, if we are at 20 Celsius, temperature is the same. Now pressure, guys, will be a very important factor, especially for the gas modeling. And state variables will be, of course, very important. One thing is state variable and means how much is now pressure, temperature, density. Now we will have trajectory variables, which are work, how much work was done here, how much heat did you spend here, and so on. That depends on the trajectory. Now we're going to talk about the laws of thermodynamics. First law, which is the conservation of energy. Energy cannot be destroyed, it can only be converted. And the interesting part right here is this equation. It says that the energy, the transit energy, which means energy that moves from one system to another, typically heat and work, are exactly the same as content energy, the energies that are contained within the matter. So enthalpy, kinetic energy, and potential energy. Now we're going to be talking about balances of common equipments, typically maybe, I don't know, a heater, evaporator, a pump, but once again as black boxes. We don't care how this flash work, we don't care how the pump works, we just need P1, P2, sorry, T1, and pressure 2, temperature 2, maybe even volume. So we are interested in modeling these state variables and let's see if there's an exchange of work or heat. But still, we are not caring on how do we operate pumps, as that was an example. Then we go for the second law, which is typically pretty similar to the third law. It's about entropy, or processes that can go in the forward direction, the reversible processes, and in the backward direction, which of course in this universe does not exist. Reversible does not exist either, but we can model plenty of, let's say, processes like that. For instance, the battery of your phone can get charged and discharged, and you can charge again. But actually, you are losing potential in the battery, and probably you know that maybe before 100% lasted for 1 day, and now 100% lasts for about 16 hours. Eventually, you're going to kill the battery. Well, actually, eventually you're going to change off battery, but If you keep using recycle and going forward reverse process, you will eventually go to 0%. That is, it will not work. Because in real life, there are no reversible or 100% reversible processes. There are plenty of frictions, which we will be studying. Now, this is very good because once we start actually modeling a lot pressure, vapor, temperatures, and very crazy processes, the good thing is we can imagine some processes. So if I tell you, let's cool down this water, it sounds fine. But if I tell you, let's do this isentropic process at this temperature pressure, and then we increase it, and we pressurize the system until we get to such pressure. So many times you're not going to be able to imagine that because you haven't experienced those processes. But it's fine, guys, because eventually, once you get the second law of thermodynamics, you will be able to say if that process is possible or impossible. So that's awesome. Even though you don't have a clue of a process, you can say if it can happen or not in real life. Now, once you are able to calculate entropy and conservation of energy and so on, we're going to analyze machines or thermal machines, which are essentially just machines that use heat and work. So maybe you want to add work in order to get heat. That is a heater. Maybe you are at your home, you have this, you plug it in, and then it starts warming your bedroom. Or backwards, which is the typical one, we want to use a fuel, burn it, and take out work as electricity. So this is essentially a cycle. We're going to use these thermal machines, we burn it, and we take out work, and then we start burning again, and so on. There are plenty of cycles. The most famous one should be Carnot, because Carnot calculated the perfect and maximum efficiency of a system. So he said, okay, let me take the most ideal cycle and I will get what is the efficiency by definition. And eventually I know that no one or no process can be better than this one. So if I get a current efficiency of 80%, then by definition, I can't go further than 80%. So if you are working maybe 79%, there's not that much to do. You can leave it as it is. So that's good because we have a reference point on efficiencies. Imagine you are working in an industry and you have a process that works at 60%. Well, you will want to increase it, but maybe that 60% is already the maximum Carnot cycle efficiency. So then you will say to maybe your boss that we cannot go further because we are already in the maximum thermodynamic, let's say, potential. Now we're going to analyze energy generation plant, and I hate this word because generation means creating from nothing, but actually is not. From first law, we cannot create energy. This is essentially just energy created from fuel to a turbine, and the turbine moves, spins. We have this electric stuff, and then it makes electricity. Then we got this refrigeration, which is, of course, you can have as an example your fridge. You have this machine, which is a compressor and takes out heat. So probably if you go behind your fridge, you will see this is hot because, yeah, you cannot do that. You cannot take heat without having another reservoir in which you are heating up. Now we start analyzing, probably this is also different than many syllabus. Rankine, Carnot, Brayton, internal combustion, diesel. That's very up to your university. I will say at least Rankine cycle is a must. Carnot definitely is a must. This is theoretical, Rankine is practical. All these other guys are also very common in the mechanical industry or in the energy generation industry, but as a chemical engineer, I think it's fine if you don't analyze that much. The diesel engine, the internal combustion will be nice because I think it's very important to know how the internal engine works. And then finally, I think it's one of the most boring parts because it's so abstract, but maybe you like it, is the thermodynamic properties that came from Maxwell equations. So Maxwell said, okay, let's literally do all type of derivatives with respect of each other. So we have plenty. Some make sense. So for instance, the derivative of Q with respect of, I don't know, temperature is equal to C. And you will see that this constant actually is the equation of heat, means Q times a constant, which we don't know, times the change in temperature will give me the total heat. But there are many that actually don't make that much sense, or at least you cannot model them. But there are many that came from there, such as the Joule-Thomson coefficient, the thermal compression coefficient, volumetric expansion, and so on. So that helps a lot to understand and discover new applications for these, let's say, set of derivatives. Now, that was the what. Now let's talk about the why. We're interested because we want to do energy balances in units. We want to make design and calculations so if I tell you this turbine works at 80% output, well, you need to recalculate the amount of water you need. So you say 100 kilograms will give you maybe 10 joules. Well, actually, you're not going to get 10 joules, you're going to get 8 joules. So you need to adjust and increase this in order to get the 10 joules. It also helps us, once again, to know the direction of a process. That's actually very useful when we're talking about equilibrium or reaction equilibrium. Your reactor is right here. You want to know if it's going to go in the forward direction or the backward direction. Also good for substance identification and its properties, know boiling points and diagrams, a lot of enthalpy, temperature, also entropy, temperature, and so on. You have plenty, also pressure as well. General compressed flow, such as compression, expansion, cooling, heating. I mean, this is typical processes that we will be doing in the industry. Cooling stuff, heating material, expanding, I mean, the contrary to a compressor, and this is done by a valve. So we have this valve, so this is high pressure. We bring it here and we lower the pressure. Or even this, we have a very, goes here and very high speed, low pressure. Also about the thermal machines, if you go to an industry that is related to burning fuels, coal, I don't know, even a train, steam machine, whatever it takes about fuels, fossil fuels, it burns and takes out work, you're going to need this. Also for refrigeration systems, once again, electric generation, a heat pump design is also interesting. So once again, understand more about why can't we achieve the 100% efficiency, and what will be a very, let's say, high efficiency according to thermodynamics, which has a lot to be with the hot and cold temperatures you're working with, and plenty other thermodynamic properties that you will derive from Maxwell equations. So guys, I just wanted to tell you I have this online course. I haven't finished it, so I got plenty material online. You can check out my thermodynamics playlist here. You can watch it here. It's Thermodynamics by me, the Chemical.Engineering.Guy, and they are all in order, so you just need to go and click play. I think I got about 150 videos. You want to study, you should check it. We talk about diagrams, pure substances, introduction, enthalpy, and so on. So that was everything for thermodynamics, guys. See you in the next class.